Okay, we're ready to talk about the properties of rational exponents, and we're gonna like I said before, you learn these rules first in Algebra 1, but this will be a good refresher on exponent rules. You might want to pause a lot and write these down in your notes. So when you have same bases and you're multiplying, you add the powers. If you're taking a power to another power, you multiply. This is called the power of a product. So you're multiplying these two things and they're both raised to the same power. It's the same thing as a raised to that power times b raised to that power. Negative exponent, you take the reciprocal of the base and the exponent becomes positive. The zero exponent rule that anything to the zero power is equal to 1, as long as a is not equal to 0. And the quotient rule, a to the m divided by a to the n, you subtract the bottom one from the top one, the bottom exponent from the top one. And then this last one is called the power of a quotient. If you have a over b raised to the m power, it's the same thing as a to the m power divided by b to the m power, given that b is not 0, because you can't divide by 0. Let's do some examples of the kind of problems you're going to be experiencing in 5.2. So you're going to be doing a lot of simplification. This one is 7 to the 1/4 power times 7 to the 1/2. Remember that when you multiply same bases, the exponents gets added. And I know that 1/4 plus 1/2 is 3/4. This is the rational expression, and this is in radical form. Remember, the denominator is the index of the root, the numerator is the power. Okay, this one exemplifies the power of a power rule. So 6 to the 1/2 times 4 to the 1/3. Let's just take these separately. 6 to the 1/2 squared times 4 to the 1/3 squared. 6 to the 1/2 times 2. 1/2 times 2 is 1. 1/3 times 2 is 2/3. You wouldn't really put that 1 there. It'd just be 6 times 4 to the 2/3. And then this one, notice that these are both the same, so I can combine the 4 times 3, which is 12. And this is raised to a negative exponent. So I'm going to take the reciprocal of this, which is 1/12, still raised to the 5th power, raised to the 1/5 power, but 5 times 1/5 is just 1. So that would be 1 over 12 to the 1st power, which is equal to 1 over 12. So remember the quotient rule. This is really 5 to the 1st power over 5 to the 1/3. And when we're dividing, we take the second or the bottom exponent and subtract it from the top. 1 minus 1/3 is 2/3. This is rational form. This would be in radical form. And sometimes the directions will be specific on how they want you to answer the problem. Okay, so now we have, notice that these exponents are both the same. That means I can combine these. And 42 divided by 6 is 7. And they're both raised to the 1/3 power, or these are raised to the 1/3 power, so is 7. And then squared, 1/3 times 2 is 2/3. Rational form, radical form. So this time we're going to look at a couple properties of radicals, meaning, remember that symbol. If it has that symbol, it's called a radical number, a radical term. So if you have the nth root of a times b, it's the same thing as the nth root of a times the nth root of b. Same with division. If you have the nth root of a divided by b, It's the same thing as the nth root of a divided by the nth root of b, given that b is not equal to 0. So for example, notice that the indexes are the same. That means I can combine what's inside there when I'm multiplying. So this would be the third root of 12 times 18. 12 times 18 is 216. And I know that 216 is a perfect cube. And the cubed root of 216 is 6. Division, notice the index numbers are the same, so I can combine those. 80 divided by 5 is 16. The fourth root of 16 is 2, because 2 times 2 times 2 times 2 is 16. This is rather a long section. There's a lot of, looks intense, but most of this is stuff you guys already know. You already know most of these rules. So you're going to have a section where they're going to say simplify, put in simplest form. So what we're looking at, I have the cubed root of 135, and I want to see if I can factor out a perfect cube out of this. Well, I know that, actually I didn't know that 27 went into 135. I had to use the calculator. But I know that 27 is a perfect cube. And 27 times 5 is 135. So now I can simplify this one step further, because the cubed root of 27 is 3. And then you just write down whatever's left over. And what's left over is the cubed root of 5. Okay, let's look at one where we're dividing. So one thing that you need to get pretty good at this chapter is called rationalizing the denominator. What that means is you don't ever want to give your answer with a radical number in the denominator. And I'm going to show you how to rationalize the denominator. So here we have the fifth root of 7 divided by the fifth root of 8. I need to multiply this times something so that I get a perfect fifth root. Does that make sense? Maybe it will in a minute. So I know that 8 times 4 is 32, and the fifth root of 32 is a rational number. So if I multiply the denominator by the fifth root of 4, then I also have to multiply the numerator by the same thing. Because remember, multiplying by 1 doesn't change anything. So the fifth root of 7 times the fifth root of 4 is the fifth root of 28. And as we've discussed, the fifth root of 32 over here is 2. This is the answer that they're going to want. The next section will be on radical expressions in simplest form. All right. So notice now that the denominator not only has a radical number in it, it's also a binomial, right? Do you remember last chapter when we were talking about rational zeros or irrational zeros of functions? Remember that if 5 plus the square root of 3 was a factor of my function, then 5 minus the square root of 3 was going to be 2. Those are called conjugates, conjugate pairs. So you're just going to multiply this by its conjugate pair, which is this right here, 5 minus the square root of 3. And I'll show you why. So if I'm multiplying the denominator by that, I have to do the same thing to the numerator. 1 times that is just 5 minus the square root of 3. Let's see. Okay, so this is 2 binomials. Remember, if you FOILed this, you would have 5 times 5 is 25. And remember that because this is plus and this is minus, but all the other terms are the same, the O and I products in FOIL are going to be 0. So then I just have to look at the last products. Plus and minus would be minus. The square root of 3 times the square root of 3 is 3. 25 minus 3 is 22. And this would be the answer they're looking for because they don't like radicals in the denominator. Seems like a lot of work, seems a little complicated. It's not. You'll get used to it. It'll get easier for you. So adding and subtracting like radicals and roots, you can only add and subtract if the index numbers are the same. And then it's just like, I don't know, treat it like a variable. You have one of them, somebody gives you 7 more, now you have 8 of them. So because this and this are exactly the same, you have 2 of them, I give you 10 more, now you have 12 of them. So the adding and subtracting, pretty self-explanatory. Until then we get to something like this. These are not the same, so I can't subtract 2 from 54. That doesn't work that way. But I can rewrite this so that there's a perfect cube in there. Because I know that 27, this is really 27 times 2. So I'm going to rewrite this term to this right here. So now I have the cubed root of 27 is actually 3. I'm going to pull that out. So now I have 3 times the cubed root of 2 minus the cubed root of 2. Well, if I have 3 of them and you take 1 away, now I have 2 of them. You're going to see a lot of these simplify the following variable expressions. Sorry about that. Okay, so here, and for this example, we have the cubed root of 64y to the 6th power. A couple things I want you to start looking for. First of all, you should recognize that 64 is a perfect cube. You should know that already. And because this exponent divides evenly the index, I know that this is a perfect cube. All right. This is really how the book suggests it, but I think it might even be easier just to do it, let's see, this way. I know that the cubed root of 64 is 4, and I know that this written in rational form would be y to the 6 over 3, which is really y squared. So this whole thing simplifies to this right here. All right, here's an example from the book. We have the 4th root of x to the 4th divided by y to the 8th. I can separate those out because of the quotient rule. And I know that the 4th root of x to the 4th is x. We'll talk about the absolute value part of this when we do more examples in class. And this would be the 4th root of 8, y to the 8th. But I also know that that's really 8 over 4, which is y squared. Y to the 8 over 4 is really y squared. All right, here's another, nope, I already did that one page, sorry. Okay, so now we're going to write variable expressions in simplest form. Okay, the thing I want you to look for here, this looks really daunting, doesn't it? Like, oh my gosh, how are we going to do this? I want you to just concentrate on one term at a time. Okay, there's nothing I can do to simplify the 4. I'm just going to rewrite it. But because this number is greater than this, I know that I can get an a to the 5th and an a to the 3rd. If I multiply those two, don't I get a to the 8th? So that, I'll show you why I did that in a minute. B to the 14th is really b to the 10th times b to the 4th. And c to the 5th, we're just going to leave it there. Okay, one more simplification. So here's how I would do this. From this point right here. the fifth root, 4 stays in there. The fifth root of a to the fifth is really a. So I got that one out. The fifth root of b to the 10th is really b squared. So I got that out. And the fifth root of c to the fifth is really c. So that's gone. And now all I do is write down what's left over. 4 is left over, a cubed is left over, and b to the fourth is left over. As long as these exponents are less than your index number, then you know that you've simplified it as far as you can. If these exponents are larger than this, then you know you're not done yet. Okay. Now let's do one where a division problem. Remember, we don't like these radicals in the denominator, so we're going to have to rationalize the denominator. Okay, so I'm going to multiply this. Hang on a second. Sorry about that. All right. So notice that my index number is 3, and this is 8. But I want y to some power where that power is going to be divisible by 3. Well, 9 is the closest number that's divisible by 3. In order to get from y to the 8th to the y to the 9th, I'd have to multiply it by y, right? So whatever you do the denominator, you have to do the same thing to the numerator. That's what the new numerator would be. This would be the cubed root of y to the 9th, but 9 divided by 3 is really 3. So the new denominator is y cubed. This and this are saying exactly the same thing, but this form is more acceptable because the denominator has been rationalized. Okay, here's a fun one. If you were to look just at that problem right there, I know that some of you, your heads might explode, right? But what I want you to do is start looking at these problems one thing at a time. First, we're going to look at the constant term or the coefficient, and then we're going to look at the x term, the y term is by itself, and the z term is by itself. So it's like peeling an onion. You're not going to look at the whole onion. We're just going to look at one peel at a time. 14 divided by 2 is 7. This is x to the first divided by x to the 3/4. But I know that in division, we subtract the bottom exponent from the top one, right? 1 minus 3/4 is 1/4. Y doesn't have anything to compare it to, so it just stays y to the 1/3 power. And z, notice how it's in the denominator of this problem, but it has a negative exponent. So that means that we have to find the reciprocal of 1 over z, which is just z, and then the exponent becomes positive. So just do one thing at a time. Don't try to look at the whole problem because it's probably going to get you really confused and possibly angry. That's it for 5.2. Oh, and by the way, we're going to skip the video for 5.3 because everything on that page is going to be done on the graphing calculator, and we will go over all of that in class. So you will not have notes this week for 5.3. All right, we're done.